All right, guys. So it's 1:30. All right, so we're gonna continue again with this. Okay, so are there any questions before I continue with our discussion? You guys can hear me?
Yes, Professor, we can hear.
All right, great. All right, so I'm going to continue here. All right, so we stopped here at this point, right? Importing the data, right? So in this example, we're going to keep it simple. We are going to just look at how we read the data before, right? So we're going to take the exact same approach that we took before of just reading the MNIST data. Obviously, on your homework assignment, you're going to read NLP data, and so you're going to have some functions there that allow you to read text. What's nice about those functions is that the next topic next week, word embeddings, will use some of those functions as well, so, or that approach at least. And so that, you know, this example homework will give you a little bit of intuition for the next topic, which is, you know, word embeddings. Right, so as we can see, reading the data is exactly the same. We're going to import our data from TensorFlow, examples, tutorials, MNIST, right? We're just going to read the data just like we did before. And, you know, the labels are already one-hot encoded. So remember that your data has to be one-hot encoded. So here, we read the data, you know, you can see that, and then we set one-hot to true. So that way, our data set here is ready to go. Okay. Once we do that, keep in mind though that the dimensions that we have in there will need to be adjusted, right? So we need to adjust those dimensions. And the next section we call the core functions that define the RNN deep learning model. Calling the core functions is basically what we've done in all of our previous examples before. Notice we have inference, loss, training, and evaluate, just like before. And all of these are exactly the same except for inference. So inference is the one that changes considerably. And so, but it's actually, once you get it, it's not really that difficult to understand. Okay, so I'll kind of quickly go over the other functions just because we have seen them so much at this point. Okay, so the main idea is still the same here, and the only thing that changes is the architecture in the inference function. So notice that this inference function takes XTF, right, which is our data that we are feeding to the model. You know, and now I've given it, then instead of inference, you know, I called it RNN. You can call it RNN inference, inference RNN. It's really up to you. Notice here that RNN will still get output. Only outputs now could be a sequence if you wanted it to be. Then we call loss deep RNN. Notice that this takes the predicted versus the real data and compares it. That gives you the cost function. Then we have the training, and the training uses cost, right? So just like before. And then we end up with, in our computational graph, we end up with the node train op, right? So that's the node that we have here. It's train op. Okay, and then finally our evaluate is exactly the same thing we've done before. We have an output and we have a YTF. Okay, just like before. Remember, this is the standard evaluate for just accuracy. But you can still use the other functions for precision, recall, F measure, etc. Notice that the variables are the same ones that we have used in previous chapters, such as XTF, right, for the data, and YTF for the labels. Okay, so that hasn't changed either. The four functions are still also referenced with the same set of variables: outputs, output cost, train op, and eval op. Okay. All right, so now let's go, you know, really quickly through all these functions. Pretty much loss deep, you can see it here in the code. So this is although the name has changed here, it's exactly the same loss function that we've seen in all the previous videos. This is the predicted data, the real data. And then we use softmax cross entropy with logits. So no difference there. The same applies for the training and the optimizer. Notice here that we're still using the Atom optimizer with the defined learning rate from above. And here the evaluation is exactly the same evaluate function for accuracy that we did in all the previous examples as well. As you may have guessed by now, so we got the best for last, right? So the next section will discuss the inference function for the RNN. And this is the critical function where we define the architecture of the recurrent neural network. And for your homework assignment, you will have to basically adapt that problem to this code, all right? So, I'm going to give you a link online to something that's going to help you quite a bit, right? So it'll help you a lot. And my goal is to, that you understand how to apply what we discussed here for MNIST to an NLP problem, right? That should really help you to see the, understand the differences, etc. All right, so as you might imagine, the RNN function is where we define the architecture of an RNN. Generally speaking, an RNN can be thought of as a regular neural network, except that it now has the additional behavior of recurrence, right? Recurrence. So recurrence is something like, instead of continuing like that, it keeps doing this, right? Keeps doing that, right? And so this is something that is built into RNN. So thankfully, whether our sequence is 28 or 50 or 100 things in a sequence, we don't have to create every single layer. Instead, we have the RNN neurons basically that allow us to do something like that. Okay. Here's the basic scenario, right, of an RNN model, right? So you have, you're trying to predict, an output. You have an input over here, right? You have an input over here, and then you have basically this idea of recurrence here, right? You're trying to build, now notice that one layer times the parameters gives you the next layer. Just like here, you have this layer, you figure out the parameters, and it gives you the combination of those two gives you the next layer. Just, here we go back, we go back to the same operation we've been using before, which is the matmul operation. Okay, so we go back to matmul over here. So matmul is the main operation that we continue to use as we are building our RNN models, okay? So I'm going to continue here. All right, so the architecture of an RNN model can be expressed with the following equations. Now, if we break this down, basically we're saying that the output T, right, times some set of parameters Y that are the parameters between Y and the previous layer, given some activation function phi, will take as input the previous layer. Okay, the previous layer for time t. Okay, so that's the basic definition of what we're doing here, right? Just like we did before. Now, where ht can be defined here as follows. So you can imagine that this ht located here is actually this one. Okay, so that in itself can be ht equals some set of parameters, theta for alpha, given an activation function phi, and this takes the previous layer ht minus 1, okay? And then plus theta x xt. All right, so it basically takes out, you know, it takes out the previous x parameter, and then it, you know, it connects it to the hidden layer, and then that hidden layer is connected to the next hidden layer, right? But it's also connected to the y over here. So this is the connection to the y's. Notice that the connections to the y's are independent, and it's really only in the hidden layers that the layers are connected in sequence, right? So we can see that if I scroll down here, this is better seen in the graph. So let me. Okay, so we can see here. So hopefully this will become, let me see if I can fit all. There. All right, so the key thing is, remember, these are the outputs. These are the outputs. These are the inputs, right? Now notice that there's no connections here. Hopefully that's something that you've observed. There's no connections there. The connections only happen, you know, where you see these little blue arrows, right? So you have your sequence of inputs, right? And they're connected in sequence, right? And then you have your sequence that feed into the hidden layer. But it's important to notice that this hidden layer also requires the input from the previous hidden layer, okay? And so that's, you know, what is being captured in those equations. So if you think about it, let's go over here. All right, so we're going to look at y2. All right, so this one, y2, right? So y2 is equal to theta y, which is the parameters of that connection, and h. If this is 2, then that's 2, right? So then that becomes theta y phi ht. So that's basically, if we just want the value of this one, y2, we are connecting this y2 to this h2. You know, and remember that this hidden layer, as in all neural networks, goes through a activation function. So this equation captures this part. Okay? Then we can explore the next section. We're using 2, right? So then h2, which is this one, h2, right, is going to be equal to what? It's equal to, h2 is theta h, right? Theta h interacting with ht minus 1, which is this one. So if this is 2, this is 1. Okay, this goes through an activation function, so you can see that mapping there, right? It maps these two, right? Plus this input. This is going to be theta, theta x of x, guess what? 2, x2. You guys see that, guys? And so these two equations represent that. So to get something like this, and then if you wanted h1, then you would have to, you know, recalculate that again. So that's how these equations capture this relationship over here. Is that clear for everyone, guys?
Yes, Professor.
Okay, great. So no questions, it seems there. That's good. All right, excellent. So let's keep going then. So that's kind of the logic, and that's important because whenever you're building your RNN networks, you have to think in terms of that, right? So I've given some examples of all of it. So the following format is then to load the data into the RNN. Here, each row represents an image of 28 chunks with 28 features, as we stated before. So this is where it starts to get a little bit complex because we are obviously building and reshaping tensors and things like that. So this is your data. This is how you would feed the data into your recurrent neural network. Okay. So what are we looking at here? Well, this is pretty simple. We take X, NumPy array, make it a float, right? So that pretty standard approach we've taken. Now here, notice this is from 1 to 100. So this is the number of n samples. Okay, so that's the number of samples. Okay, and then so basically every row, this row over here is a sample. Okay, of a sequence. Okay, remember that. So here's what don't forget that every time now that you feed something to the RNN, you're feeding it a sequence. So I feed it, so let's say, the first sequence, right? Then, this one's the second sequence and so on, right? So you're feeding, things in sequences like that. Then so that, I should say this is samples. And then this is the number of chunks, right? So 1 to 28, right? And then each one is of size 28. Do you guys see that? So for instance, I'll give you this example. If I was feeding words, I would say the car is going and so on, right? So those are the words. And then this vector over here would be the one-hot encoding for that word. If I have a vocabulary of size 1 to 123, the word car might be index number 3, right? And so that's going to be, 3, right? That would be a 1 and everything's a 0. There's various ways of doing the encoding, but that's how you would feed the data. And then you would just have 100 sentences. So this would be 100 sentences, and then you would have 28, let's say, sequences of words. So you always want to be consistent, right? I know sentences vary in size, but you can think of it as tweets. So if you don't have the 100 and what is Twitter? How many characters is that thing per tweet? Anyone know? No, nobody knows? All right, so let's say it's 200 characters. So then you would have 200. If you don't have enough, you pad it. And if you have too much, you like truncate it, okay? But they definitely have to be the same size. So hopefully that makes sense. Just like here, they're all of size 28, okay? And then just keep in mind that you're feeding the sequence here. The car is going really fast or something. Is this part clear? Guys, so these are the parts that are a little bit difficult in this model, okay? So again, going back to MNIST, we have 100 samples, 100 sequences basically. One row is the sequence of images. So if you think, can I write? Yeah. Oh. So that doesn't work. So if I have the image over here, right, I slice a piece, that becomes that. Then I slice another piece, that becomes that. Slice another piece like that. It's going kind of like that. Make sense? All right, so if I get no questions, I'm going to assume everything is clear. All right, so that's reading the data. A lot of this, will stay the same, as I said, from the previous implementations. We still have declarations of W's and biases, and we're still using mat-mul. So, we're still performing the mat-mul operation. Okay. Now, we're going to, if you remember from the libraries, we imported the RNN.RNN function there. Now, there are several of those functions, just like there are several RNN cells, okay? In this example, I'm only using one, but you guys can use other ones. I think the homework changes those cells slightly, but they pretty much can be used the same way. All right, so this function helps to create the RNN module, which uses a standard thing called the LSTM cell. Okay, so the LSTM cell, which stands for the long short-term memory. Basically, you know, that's just based on some research. I'm not going to go into describing what long short-term memory is. I don't want to overcomplicate things. So we're just going to, you know, we want to understand the architecture and just basically at this point, be aware that LSTM models do really well in the literature. You know, that, you know, they kind of have this interesting structure underneath, but we're just going to use it as is, right? For our purposes, the goal right now is really just to run data or fit data and build the architecture of our model. And, you know, that's not necessary at this point to build the architecture. All right, so we have gotten at this point to one of the most critical parts of the process in the RNN model, okay? This is one of the most critical parts, which is about understanding the inference function, which will define the architecture. Okay, so we're going to define the architecture. So let's go through this code line by line. Okay, we're going to go through it line by line. So the first one, as you can see, is defining the weights and the biases. Okay, so you can see here, it's just simply a TF variables. They're initialized as TF random normals. Okay, and as you know, if you notice here by the dimensions, these are the weights and biases that define this part of the model. So remember, we have a model like this, right? And then we have the hidden layers, and then we have the outputs, right? We have the outputs, the Y's. These are the X's. And then this is connected like that. This is connected like that. This is connected like that, right? And so on. So really, if you think about it, this weight and bias is defining what? If you look at the bias, is size 10. So that means 1 and 10. 1 and 10. You see that? All right, and then over here, we're defining 128 to 10. So basically, we had said, that this is of size 1 to 128, 1 to 128, 1 to 128. Excuse me. That's how we had defined it, right? So the hidden layer here is that, and this is the 10. So basically, we're defining W's here, right? Those W's and the biases would come out over here. All right, so pretty standard there. Actually, this looks a lot like a regular neural network. Okay, that should look a lot like a neural network. All right, so that's done. We understood that, right? All right, the next step is we are going to take the X data, notice over here, the X data, and we can reshape it, all right? We can reshape it so that we feed the data in here. And we use here one of the utility functions called the transpose. Now, you don't always have to do this like this, okay? This is just one example, okay, of performing a transpose. So basically, we read our data initially, right? And it looked like this, 1 to 100, 1 to 100, and then 1 to 28. And then it's kind of like that, right? And this is also 1 to 28. Okay, and then we have 100 samples of this. So we have, so actually, hold on. We have an initial tensor of a shape. So let's just write it like this. We have an initial tensor, I think, of size 100 by, no, it's like this, 128 by 28. Okay. And then we have, okay, so we have 100 by 28 by 28. Yeah, so well, let's take a look at this down here. So let's just go over the discussion. So one of the main issues or requirements with the code in the RNN function is that it needs to reshape the data so that it's compatible with the requirements of the RNN architecture. So now let's focus on the transpose. So in the previous code example, code segment, we can see that the data is being transformed via operations such as transpose, reshape, and split, which are these: transpose, reshape, and split. So notice there's parameters there. Initially, the X variable has the initial shape of 100 by 28 by 28. Okay. So it's, it's like 100. So yeah, so it has a specific shape. Now we can transpose it. We can do the operation, the transpose operation of X given these parameters. And basically what we're specifying here is the index position. So we're reshaping this, like, it goes from 128 and 28 to 28 by 100 by 28. So the transpose will transform the X shape into the following shape, right? And you can see that basically we're saying move position 0. This is 0, 1, 2. So we're saying move position 0 to the middle. So the 100, right, gets moved there. Move position 1 here, right? So then this becomes 28. And then leave position 2 at position 2, so 28. So that, basically we just reshaped the tensor a little bit, okay? And that's just because that's the way, the data is fed into the RNN, okay? So that's the way that, the data is fed into the RNN. We have 100 sequences. We have 100 samples. We have 100 samples where those are sequences of 28, and each one of those 28 has a shape of 28, okay? So that's basically the approach there. Okay, then we're gonna reshape this, okay? So we're gonna do a reshape from there, we reshape the X, and you can see we take the X, we're gonna get a new X, and we just infer that dimension, so we kind of make it two-dimensional in this example, right? So we're going to make it two-dimensional here. So this results in a 2800 by 28 two-dimensional. So we made this one into that, and that's just because these two get multiplied, right? So 28 by 100, and we get this shape, okay? And then finally, we can split this again. Okay, so we can go down over here. And now we're going to split the data. Or sorry, here we're going to split the data. And this will result in a shape of 28 by 100 by 28. Okay, so that's really the way that, this expects the data to be. Okay, in this shape, I would, I think it's 28 sequences. There's 100 of them, and then each one is of size 28. Okay.
Professor.
Yeah, go ahead, please.
So why did we perform a transpose on our data? Because
what's happening is, and this is probably best seen when you print out the data, is that it needs to. So let me put it this way. It's like the data is like this, right? But it needs to be like this to be fed into the RNN. So it's probably that, the tensor wasn't in the appropriate shape. You know what I mean? So like initially it was 100 by 28 by 28. So that would have meant what? Maybe like this. and then maybe like that, right?
Mhm.
Maybe like that all the way going down. You see that?
Yeah.
So it's kind of like going down. But if we look at this one, what would this one be? This one is 28, right? 28 by 100 by, help me out. So how do you draw?
Yeah, that's why like I'm confused. Like we are getting reshaping back again to 2018 and 128.
But initially though, it's 100,
Yeah,
28 by 28.
28. Yeah, and then we
And
reshape.
now it is, so the way that I see this is that it, in a simplification, it was, the data is like this, but it has to be fed like that.
That's what the transpose does, right, Professor?
Yeah, you just reshape, at the end of the day, you just perform all those operations to arrive at this.
And why can't we
Sorry,
just,
not that one, arrive at this one.
so we right now, like earlier, like we have an initial shape of 128 by 28.
Yes, you have 100 samples. If you remember, that's just coming from the X. So let me go over here. So remember, it's the way that you read the data. So if we had read the data in the way that the RNN needs it, we wouldn't have to reshape it. You see that? But we read it in a different order.
And now
So
after
here,
that, we perform a transpose.
it's like, they go down, right? This is the X matrix. So it's 100 going down. It's 28 this way, right? And 28 depth. Yeah?
Yeah.
Yeah, right. So this is how the data is. It's like the slices are there, right? But we need to
Reshape it.
just reshape it basically, right? So if we do the other one, if the other one is, what was it, 28 by 100 by 28, what would that one look like? So it's 28, 1 by 28. And then this dimension is 100. You see that? And then the depth dimension is 28, correct? Correct me if I'm wrong, guys. You see, so although it's seen, remember that everything here is linear algebra, right, Sumendra?
Yeah, Professor.
And so we can't sometimes give the data, it's not like we can give it like this or like that, and it's gonna figure it out, because at the end of the day, sequences could be different. The sequences could be 100, and we only have 28 samples. You know what I mean? But in this case, sequences are of 28, and they are 100 samples.
The what confused me, Professor, is like
let me just go with this idea. So this will make sense to you, okay?
Okay.
Sumendra?
Yeah, Professor.
All right, so think of it this way. We need to give it, according to this code, right? We agree that it has to look like this. This is what the data that we get, right? That's the initial tensor. So we do all those operations to reshape it to this. If we fed it like this, right? What would it think? It would think that there are 28 samples,
Okay.
but the sequences are 100 steps long. Whereas here, if we feed it like this, there's 100 samples, but they're only 28 steps long. You see that?
Mm-hmm.
So this one has the right dimensions, not the other one. Is that clear?
Yeah, and then we reshape it back again, right, Professor? To 2800 by 28.
Well, We didn't actually. I understand your question. And
Yeah, that's why I get confused. Like why we are doing.
why
this.
did we go back to the same thing?
Yeah.
Okay. I'll show you. Because we didn't perform a third reshape operation. We performed a split.
Okay.
Does that make sense?
So now we have 2800.
So we end up with, it's a good question. We end up not with a tensor anymore, but we end in the split, that final split, we actually end up, and I should write that in my book actually, we end up with a list of tensors now. You see that? So here we can see this is a tensor, right, Sumendra?
Yeah.
That's a tensor of 3, D3. This is a tensor of D2, right? So,
Yeah.
so far, these are tensors, no problem. Would you agree?
Mm-hmm.
But the last step is not a reshape. It is a split. So you see here, we do TF.split, right? Basically, now we end up with a list of, it should be a list in that shape, you know, so I'm not drawing the shape how it is, but it's a list of sequences of 28. One, two, three. And this is what, 28? And it's a list, and they're basically all of size 28 as well. Except that they needed to be in whatever that shape was that we had before. Make sense?
I'm still confused on this part, honestly, Professor.
On which part?
This transpose part, like after we transport it, we just make it in 2D, and then we again go back to the third dimensional again.
But we split it. So before we had one tensor, now we have 28 tensors in a list. You see from here, this is one single tensor of 2800 by 28. You see that?
Uh-huh.
But after the split, the list is not a tensor, right? And it's made up of little tensors, right? So it should be, we split it into 28 by 100 by 28. So, which was, what is it? We said it was 0 to 28. And then this is the long one. So, right, 100. And then these would go and be 28 themselves. So basically, this should be 28 sequences. So the sequences would go down, right? 28 sequences, and each one is a feature vector. So that's what it takes. This is one sequence. Then the next one is another sequence. And the next one is another sequence. And the next one is another sequence. You see that?
Mm-hmm.
Does that make sense? But they're not a tensor anymore. They're basically then, that's one. That's two. That's what we did. In the split, from the split, we go from that to that.
Okay.
Dot, dot, dot.
Now each one is an individual tensor now.
Yes, they are individual. Remember, a tensor can be a scalar, it can be a 2 by 2, a 3 by 3, it doesn't matter. But the way it just the RNN needs it, you know, it doesn't take like a single tensor, right? It takes a sequence of of this data basically. You see that, Sumendra?
Yeah.
Okay, so it's a great question. So let me summarize it here. Okay, so let's go.
Professor?
Yeah, go ahead, Alam.
Professor, I didn't understand the split part, like the last one TF dot split.
Okay, so let me go over it again. Okay, so let's go over it again. All right, so notice here, right? So we created the W and the bias, right? Then we have these three steps. We have originally the data in X looks like this, right? So when you guys, so I recommend when you guys run this code, check out the shape of this. Just check out, you know, the shape of these objects, okay? So start with X, okay? And the way this looks here, is there's 100, right? 100 of these, and then there's 28, and then into 28. So I would say it probably looks like this one. Goes down to 100, then to 28, then to 28. You see that?
Mm-hmm.
But we need to change that dimension, right? We need to reshape the matrix. So we go
Can
down.
you say, Professor, we
Yeah,
are
go ahead.
slicing basically?
Say that again?
Can we say that like we are really slicing now?
We are not slicing. We are only reshaping the tensor. So remember that in linear algebra, you can't always like multiply two matrices if they don't have the right proportions, all right? So that's why you have something called a transpose. The transpose over there, it's basically a way to like make, you know, flip. So it's a linear algebra thing. Let's say that you have this, and I transpose this, and now I flip it. The whole matrix. Do you see that?
Mm-hmm.
It's a type of operation like that. And so that's what we're doing here, is because if not, the multiply, okay, so maybe if I say this, it'll make sense. So if I multiply this, right? Or if I multiply this, and this is X, that's X. This is, let's call it W, but I make W of that shape. You see that it's exactly the same one.
Yeah.
They're exactly the same one. But I do a matrix multiplication in linear algebra of these two. This one would work. This one will not multiply.
Yeah, because of their dimension.
Because of the dimensions. In linear algebra, they need to have, you know, specific, you know, rank order, you know, and so it's just a linear algebra thing. And so remember that what matmul does is basically
basically a matrix function, right? Matrix, you did a matrix multiplication earlier, and
yeah, we're gonna do a matrix multiplication because we have to take the X and the W, right? And everything, you know, to do the operations.
And that's how the shape is changed now.
Say that again, sorry?
That's how the shape is changed of the W. The shape of the W is now changed.
The shape, yes. So all we're doing is we're like flipping it. So maybe we receive the data like this, but we need to have it like that. And so that's why we transpose it.
Okay.
Make sense?
Yeah.
Yeah, so the example I was using is this one, right? So I'm saying the data looks like this one, like this matrix. It's a 100 by 28 by 28. That may not align with what we have in the equations. And so we transpose it to look like that. It's still the same data. Nothing has changed there. It's just flipped. Okay? Mm-hmm. And so it's going to be now 28 by 100 over here by 28 in depth. So that's the first step that we do. So if I go down here, you can see that's all I'm doing, right? So I'm doing this transpose over here because I'm feeding all the data at once. It's basically like I'm feeding data in batches, right? And that's really what's complicating things is the fact that I'm reading the data in batches. once it's in the right shape, now I want to do the split, but before I do the split, I'm going to reshape it. And if you guys remember from the previous lecture, we just said that the -1 infers
The best size.
dimension, right? The last dimension, so it'll figure out take the other two dimensions and make it into one. Okay?
Mm-hmm.
And then the last part, that's still gonna be just one single tensor. I don't know in what shape, but let's say like that. But we still need to split it because we need to have several little tensors in there. You see that?
Mm-hmm.
Commander?
Yeah, Professor.
Okay, all right. So that's why we do that part. And then I'll come back to this in a second, but let's just finish this. Okay, so if I go down here then, so one of the main issues is we need to reshape the data so it is compatible with the requirements of the RNN architecture and model, which basically means it can do the matrix multiplication, right? So in the previous segment, we can see the data is being transformed via operations like transpose, reshape, and split. So initially, the X variable has an initial shape of 100 by 28 by 28, but we're going to transpose this. So we're going to flip the values, right? So, 100 now becomes that, then this is 28, and this stays 28. So we basically just flip these. Okay? And that transposed it, so that gives us something like this, right? So we have, oh, no, that was for the split. So we flip the data, and now we do 100 samples. So this now looks like, oh, it has an initial shape of this. We transform it with the transpose, and it now gives us that, which is the 28 by 100 over here, but 20 by 28 in depth. So it ends up basically looking like that from looking like this. You see that, Alan?
Yes, sir. Yep.
You see that? So initially it looked like this. Now it looks like this.
Oh, okay.
Because remember, as I said to Samendra, it's a linear algebra thing, a matrix multiplication thing, right? And so you just want to have the right shape. So just think of it that way.
Okay.
You could have avoided this step if you had read the data like that, for instance.
Yeah.
Okay? And then once you end up with this, okay, then you do, then you're going to make that three-dimensional one, just like we've done with CNNs, into a two-dimensional one, right? And so that's the reshape step here that just makes it into that. So now we take the 28, we take the 28 by 100, right? And now we get a grid basically. So it's gonna be now 2800, right? So it's gonna be this. So it's gonna be like 2800. We ended up with that. You see that? At two dimensions, it's two-dimensional. So this is 1 to 2800, and then every row that we have in there. You guys see that?
Yeah, bro.
Okay, and then the final step is this split. Okay, so we're gonna do a split, and now we're gonna say, I want you to split it for the first dimension into chunks of 28. So it's gonna take the 2800, 1 to 28, right? and it's going to basically do it, split it into chunks of 28. So it's gonna have this, right? So we're gonna end up with, we would end up with a list basically. 28 now, how it looks in the list, it's gotta be like this. So it's gotta be, let me think about this. So it looks like this currently. We're gonna get 100 of these, right? For the 100. So basically the first 28 are one sequence, then another 28 are a sequence, another 28 are a sequence, dot, 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 until the last sequence, but there's 100 of these. Would you agree?
Yeah.
And so basically that would mean that actually, yeah, this creates a list which is needed. Yeah, so maybe don't look at it like this, right? Don't look at it, because I think that's what's misleading here, is that by writing it like that, I've written it like a tensor, right? And so the way that you should think of this is that you end up with a list of 100 of these, of size 28. And they're actually, they should be, they are grids, right? Yes? So that's really what you should end up with from 1 to 100. Do you see that, guys?
And Professor, that grid is by 28 by 28. Each cube is 28 by 28.
Say that again, sorry?
Like each cube in the list is 28 by 28.
These are no longer cubes. These are only grids because they are now the sequences of 28. They're the sequences of 28 where each one is 28. Because remember that each image is 28 by 28, right? So we're going to feed into the model. If you remember, we're going to feed in, we have a hidden Markov model, or sorry, an RNN dot, dot, dot. This is from 1 to 28, and these are 1 to 28 each.
Okay.
You see that? So really, if you take each one of these, right, they're a slice that makes up an image. You see that? You see that, Samendra?
Yes, Professor. Yeah.
Yeah. So this is really what we end up with. I think the confusion is probably, you know, I shouldn't have written that.
So now,
because this does split it into, for that first dimension, right? And the first dimension here is 2800 by 28, right? So it splits this one into chunks of 28. So it's going to give you 100 of those, given the input.
so 100 is our sample size, right, Professor?
100 is a sample size. That is correct.
And now we end up with a grid that each grid, like each cubical grid of 28 is an
Each square grid,
yeah, each square grid is a input now, a single sample.
a single sequence. It's a single sequence because remember, you don't feed one sample at a time, you feed one sequence at a time.
Okay, so now instead of like what we were doing earlier with an image in the pixels, now we just slice it in a sequence of 28.
Yeah, so the way that this ended up being is that the first sequence was here, then the second sequence, and the third sequence, the fourth sequence, the fifth sequence. But when we do the split and we end up with the list, you know, the list has, you know, it's, and I keep drawing it like this, but it's really a grid, right? And each one of these is a sequence
Those are 28.
of 28. So they're like this. Yes. Because remember, a sequence is from 1 to 28, but each sequence is a vector of size 28.
Okay, I got it now. Okay.
Yeah. So for instance, if we, you know, let's say that we had sequences of 28, but it was the bird example. We only had like 4 features, right? So this would be like wind direction, latitude, longitude, and so on.
Professor,
Yes, go ahead.
why did you put 0 in TF dot split in the first line?
This one?
0. Yeah.
Because this is the dimension where we split 0 and 1. We didn't
Okay.
split 1, we split 0. Does that make sense?
Okay. Yeah. And here X is the input in batch size, right? 100 inputs.
This X,
Yeah.
this X is the previous one. So remember that, you know, if I go back, right, I'll go back to the function here. So here we start with the original X. Let me go up here. Right, so we start with this X, but that's the X that I showed you guys. So again, that X, if I remember correctly, looks like this. Yeah? Because it's 1 to 100, but this is 28 and 28, right?
Yeah.
Goes in here and it needs to be transposed. So let's imagine that this one now becomes like that. You see that?
Yeah.
After the transpose, then this X becomes the input to the reshape, right? And then the reshape, we just take this one, which is 3D, and now we make it into 2D,
Oh, okay.
which is actually really long looking, right? So it's like this, because it's 1 to 2800, and this over here is only 28. Do you see that?
Yeah.
And then this X is this X, and now we do a split, which is different. That needs to be used from a tensor into a list of tensors, where the list of tensors are, as I said, the list of tensors is like, oh, sorry. The list of tensors is here. They're these. This is a list. And in here, what you have is grids that are 28 by 28, because each, let's say each one of these columns is how we looked at the image in sequence, right? But each one is made up of 28 features, the pixels.
Okay.
So
Is that clear?
Yeah.
Basically, we end up with a list of 100 sample with each cube with 24 rows and 24 column. That's what it is, right, Professor?
28.
28.
Yeah, 28 into 28. 28 columns with each column having 28 rows.
Yes. And that's because, remember, in this example, each one of these is an independent sample. It's a sequence, an observation that you've seen. Does that make sense?
Yeah, it's quite clear now.
Okay, all right. And if we have time, I know it's harder to visualize here because it's an image in 28 by 28. That's why I want us to look at the other problem, okay, which is that it's not going to be 28 by 28, but it's going to be, let's say, 28 by 5. And so that difference allows you to see this a little bit better. Okay? Guys?
Yes, Professor.
All right. So let's finish up the function then. So I know it, there's the reshaping of it. Okay? And that just takes practice. And then after that, so let's go back to the function over here. Okay, so we let's say once you've reshaped and you've got your list after the split, then you come into the main portion of the RNN. Okay, so we come to the main portion of the RNN here, which is going to be building the basic LSTM model. So notice that this is pretty simple. Here you just initialize the LSTM cell, right? This is what captures, remember, that whole architecture like that, right? So all of this. And you don't have to worry about it. You just know, now it has to be like that. So remember, this architecture, you kind of have to fit your data into it, okay? You can't really modify it that much. So here we build the basic LSTM. This will change in other examples. It may just be LSTM cell. This is the size of the hidden layer, right? So if you remember, we said that it was going to be, this one's 28 for one instance, this one is 128, and this one over here is 10, okay? So we build the LSTM, and then now we're going to use it. So we call the RNN, we use the LSTM that we just defined, and because our data is already fit in the right position, right, we just plug it in. That's the beauty of this, that once you fit this in the exact right direction, you don't actually have to do much in this step. Does that make sense? Questions, guys? Amanda, is that clear?
Yes, Professor, it's clear. Yeah, I got it.
All right, great. All right, so this is clear. And then once you do this, you get this one and you get states. States is like, you want to look at some of the data in the model. We really are not concerned with states right now, like middle point data. We just want the outputs, okay? That's really what we're looking for. So in the hidden model, basically, if I have the RNN here, right? And then I have this here, this here, this here, this here. And then I have the final outputs, which are independent, right? So notice that these outputs have to be these values here. You see that? Because if you think about it, you're going to take outputs and you plug that in here, and then you perform a matrix multiplication to obtain this one. Do you guys see that? Guys?
Yeah, Professor.
Like you're getting this sequence of values, right? And then each one of these is like outputs 0, 1, 2, and so on. So let's say I want like 2. Okay, I grab this one. I would plug that in here. So this would be like 2. And then I perform a matrix multiplication between the weights and the bias, and that gives me RNN output. So that would give me basically this one. Is that clear? And that's really, if you look at the weights and the biases over here, just look at their dimensions, right? So if you look at these, the bias is 10. So that implies that you're talking about the outputs, right? Because these are 10. And then this one is 128. So if you remember, we always said that weights were a combination of the 2 layers, right? So, well, this one is 128. One is 10. So therefore, this is the weights for that, which means that we take these outputs, given the weight and the bias, perform a map mul, and that gives us our RNN output. So these values over here, the sequence of outputs. Is that clear, guys?
Yeah.
Question? Okay, so that's clear. All right, no questions. That's great. Excellent. And then let me just show you here. Now, what do you think this means? Since we only give, I gave it a -1, right? So what do you think that means?
Is that the same as like what we did with the CNN, where it was like the assumed value or something like that?
Yeah, it's an assumed value. You got it right there. And basically what that assumed value means, it only gives you the last one. So because it makes sense, right? It's the question of the problem here is, what digit is it? So really you look at the entire sequence, it will predict values for these, sure. But really, the only one that matters is the last one. You see that? So this is the example of saying, for instance, you know, what's going to be the ice cream consumption on Friday if we start on Monday? Well, this is the one for Monday. This is one for Tuesday, Wednesday. This is the one for Friday. The last prediction in the sequence. And that's what you do here. So you only did a mat mul for one. What we have learned already from TensorFlow, pretty much if we didn't have this, it's gonna give us the entire thing.
So Professor, the last one will be the label.
The last one will be the label, exactly. The last one will be the one hot encoded. So the last one will predict, because this is size 10, right? So if this is a 7, 0, 0, 0, 1, 0, 0. That's a 7. Exactly right.
Okay. So actually we are training our model.
Huh?
Actually we are training our model in this function through labels like
I'm training an image in a sequence approach, but still I want to say, because we said the classes are still 10, right? So it's still the 10 classes from the handwritten digits. We still have to give it the one hot encoded label.
okay. So the last one is taking the whole vector as a one, the whole one hot encoded vector, right?
Which one, sorry?
The last one you are saying that it's taking input in the form of a vector which is one hot encoded, right?
They're all, so all of these outputs are one hot encoded. All of these are one hot encoded. They're the from 1 to 10, right? The
Okay.
digits.
Okay.
These are of size 128 because they're the hidden layers. You just define that because you want to define it. And these are, there's a sequence of 28 of these, and each one itself is of size 28. So there's 1, 2, 3, 28. But each one of these is of 128, 128, 128. You see that?
So Professor, in this code, this RNN output is our Y predicted, right?
Yes, exactly. These are the labels. Yes.
Okay.
That is your Y predicted. Yeah. But just keep in mind, it could predict the entire sequence, which basically means it would return what? It would return, instead of a single vector, it would return a matrix, right? A matrix of all the predictions again.
Okay.
Because this is sequential mining.
Okay.
It just so happens that all we care about for this one is the last one, because that's going to be the number that we predict. As long as the last one is correct, with enough data, the model will learn it.
Okay.
Got it?
Yeah. So I think then we will do the same thing, like we will pass it to the function of argmax that we did here in the previous code.
Right, right, exactly. We just get a label, and then, you know, that's pretty much it. You're right.
Okay.
Okay?
Mm-hmm.
All right, so let's finish this up then, because I want to assign the homework. All right, so we're done with this. So finally we get RNN output, and that's this one, okay? RNN output. So now I can move on to, and like I said, the code in the homework is exactly like this. If anything, I think it's a little bit simpler. Okay, so now we have the inference function created. So the next step is now to define the tensors, right? So we're going to define the tensors. All right, so creating the labels and the tensors. In this section, we will discuss the placeholders. These are the same variables XTF and YTF that we have used to load our data. However, as you can see from the code below, XTF placeholder is a bit different. It's going to be like with the CNNs, really. In the past, we define XTFs with dimensions, none, and features, right? But because this is going to be three-dimensional, so in the past, we had none and 784. But because the vectors were of size, because of this. However, as previously explained in the parameters section, we now break up each image into a sequence of 28 chunks of size 28 per chunk. Therefore, we must capture this information effectively with TensorFlow. And luckily, as its name indicates, TensorFlow can store data in tensors of size none and chunks and chunk size, which I think some of you did this already anyway. All right, so that's all we have to do. And so we're going to create our XTF, and notice here it's going to be none by 28 by 28. So it's already initially a three-dimensional tensor. You see that, guys?
Yeah, Professor.
100 samples, then of chunks of 20, a sequence of 28, where each one has 28 values. And then notice the YTF is the number of classes, which is 10. So it's also one hot encoded. Now, all that remains for us to finish our code is to define the session, initialize, and then the main loop. Okay, so let's go to that. So here, this is all the same code that we've looked at before. So initializing the session, YP metrics so that we can do the performance, precision, recall, F measure, and so on. And then now we have our main loop, okay? So again, you know, here we go. All right, so we made it to the main loop. This is the part of our, this is the last part of the code. Most of it is similar to our previous implementations, although there are some differences. And as you might imagine, the differences have to do with the shapes. The data is read in batches. One of the aspects here is that the images of size this must be reshaped to accommodate the RNN approach. Okay. Remember that we have to fit our data to this RNN model. So, you know, that's the difference. So we're going to read the data in batches, just like we read from one of our previous examples. The way that we read it from that library is that we read, if you remember, each batch X of vectors is going to be vectors of size 84, right? You guys remember that. That's how we read them. But we must reshape that data into batches of sequences of 28 chunks by 28 elements each, okay? So we achieve this by doing a batch X reshape, okay? So now we're going to, instead of, because we read it from the library as, you know, n sample or batches of 784, right? We need to reshape it to this. So now it's going to be the batch size, but 28 by 28, okay? Which kind of ends up being like that data set that we had before, right? You know, if you remember, this is where the data looks like that. Make sense? Okay, so then So we read our data. Okay. Once the batch is reshaped, it can be used by the training step, just like in previous examples. In the testing phase of the main loop, we will read 256 test samples, okay, to basically verify. So we're going to do the training and the testing. And these also must be reshaped, okay? And that's, you know, basically the same approach over here. We're going to read the data from test images to 256, and then we're going to reshape them into 2828, where we infer the number or the size of batch, right? So how many? Let's say 100 batches, or a batch of 100 images, however you want to say it. Okay? Make sense? Okay, and now we have our samples, converts the test samples into sequences of n chunks of chunk size each, which basically means we have sequences of 28 where each element in the sequence is a vector of 28. Okay, so that's really important for us not to forget. Finally, we're ready to finish the code. The main loop doesn't change at all. It's really just about from our previous videos, it's just that we have to, you know, basically, because we already, we have to do the reshaping operation. So you can see the main loop here. Same approach for the while loop until number of epochs. We read our data from MNIST, right? We get batch X and batch Y. We need to reshape it, right? So as I said, batch X has a vector of 784, which needs to be converted to a sequence. So we reshape it into this, okay? Then, so batch reshape, we give it batch size and chunk size. That gives us a new tensor, basically, batch X. Our X is a three-dimensional tensor, right? Our placeholder is 3D. And this one is also 3D. Therefore, they're going to fit, right? And so we pass that data. And then remember, when that data gets into the RNN, that's where we have to do all that transpose, reshaping, and everything, right? So really, I think the reason why we had to do the reshaping is that from this MNIST, we are reading the data as, you know, 784 by 100 or whatever. So that's really what created the complication, okay? When you have more control of reading this data, maybe you don't have to do a transpose. You guys see that? Guys? Can you guys hear me still?
Yeah.
All right, I'm almost done. All right, so basically here then, as I said, we do the reshaping operation, and now we feed batch X and batch Y to the placeholders XTF, YTF, and then we just call train up. And by calling train up, we're going to call inference, we're going to call all those functions and perform the RNN training. Here it's the same thing. We provide batch X and batch Y to XTF, YTF, but we print out cost and eval up, right? So here we're calling the train, here we're calling cost, and these are just so that if you want to look how the loss, so this is usually what you do when you want to see the loss function improving, right? So you want to see the loss going down, 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 because it's learning. Finally, you know, in the loop, after you do the training, we can do the testing. So the testing is pretty similar. We're going to take batches of 256 from MNIST test. Notice that before we took the data from MNIST train. Now we take it from MNIST test. We do samples, 256, reshape it again, right? Same thing, 28 by 28 by whatever, 256, because that's the size of the batch. And then we take the labels again, you know, these are already one-hot encoded, so this is 256. So we have test data and test labels, and that's what we feed, test data and test labels, into the placeholders. We call eval op, And that's just going to call the accuracy and give us our result. And then finally, that gets printed there. And that's how we get our accuracy. Do you see that, guys? And, you know, this is just a more explanation of reshape function. So for reshaping tensors, so we define the new dimensions as you've seen already. And that's basically equivalent to saying 100 by 28 by 28. So I think that should be obvious. Okay. And so on. So that's basically what I explained. Finally, one thing I want to recommend as you're doing your code, because I know this one has a lot of reshaping, is print out the dimensions, okay? So a good way to understand how the reshape function works is to print out the shape of the tensor before and after the reshape function. So the following code segment can help to visualize these dimensions. So you can try this, okay? So you can take, for instance, you know, take whatever your, at any point in the code, take your X, right? Calculate the shape of it. So it's going to say, if, you know, it's going to say like 100 by 28 by 28. That's what that does. And then you have it in the shape. And then just remember that because you're running it from TensorFlow, and I know we're a little out of time, over the time. Let me just, I want to assign the homework really quickly. So that shape then you run with session.run. And that will give you, when you print it, it'll print out 100 by 28 by 28. So I would recommend, you know, when you do the transpose, print this. Then when you do the reshape, print this, right? And draw it out by hand, and hopefully that'll clear up how we are reshaping the dimensions of these tensors. You know, the way that I can explain this sometimes, you know, let's say like a machine gun, right? And this is not a great machine gun. You know, the clip doesn't go like that in that direction, right? The clip needs to go there in that direction. You see that? This is an analogy of why we reshape and transpose the matrices. Is that if we have it like this and we try to like clip this into the machine gun, it's not going to clip. Only clip if it's coming from this direction. You see that? All right, and then once you run this code, which is on GitHub, you should get an accuracy, you know, really good accuracy, somewhere in the 99 range. And that's it. So that's RNNs. Okay, so unfortunately, we're a little bit out of time. Are there any questions? Before you leave, guys, I just want to assign the homework, okay? So I want you to go to a link. I want you to go to a link. And basically, you're going to do the same thing, but for this problem. So go to you're going to go here. So you can Google this LSTM by example using TensorFlow. Okay. So this code that I found online is pretty much very similar to the way that I wrote my code. Okay. And so I really want you to read this blog spot and basically solve this problem. Okay. So I like this problem because it will be somewhat challenging, but at the same time, you will have a lot of help. You can see here what we're doing is something similar. Before, we were doing MNIST images, right? In my,
Sir, can you share the screen?
oh, I'm sorry, you're not seeing it. Sorry. Oh, okay, so I want you to go, can you see it now, Samendra? Can you see it now? Guys?
Yes, we can see it.
Okay, great. So this is the, you can see the link there, right? You can see the link at the top. I will put this on the Blackboard, and also on the video, you'll be able to just look it up. There's the URL. And basically, this is an LSTM example in TensorFlow. It's very similar, almost exactly the same code that I use for the MNIST example. But what I like about this is that you're trying to solve an NLP problem. Okay, in particular, you're going to have a sequences of 3. So I'll just say this. So whereas before, oh, I cannot write on this. Okay, so as before, we had sequences of 28 where each one was size 28 here. Can you see my mouse at least?
Yeah.
Okay, now you're going to have, instead of sequences of 28, you're going to have sequences of 3. So 1, 2, 3. You have your hidden exactly what we did. And then notice the outputs would be this, but we only care about the last output, which is going to be a word. Okay? Now the outputs for us in MNIST were 1 to 10. Here, the output is you're going to predict the next word. So the car is going very fast. Or in this case, had a general counsel. All right? So you want to predict that word. So it's a very, you don't have tons of data. It's just like a very small document that you can use. And you can use any document that you want. And so basically what you're going to figure out is the number of features in this vector, okay? And so that number of features is going to be determined by the number of words in your vocabulary. So for this example, they only have 112 unique words, right? So that means this vector is of size 1 to 112. The hidden layers can be whatever you want them. The inputs, each vector is also of size 1 to 112, and the sequences are size 3. Does that make sense?
Yeah.
Okay, and so now to create the vectors and all of that, we're going to take the exact same approach that you would take in Word2Vec. So if you've ever read that code in Word2Vec, next week we're going to talk about this a little bit, but basically this function will build it for you. You create dictionaries, and I think it's really well explained here how they do it, okay? So you can see the diagram here. This is a vector of 112, and it basically says that this is the word that has the highest likelihood, 37. Well, it just so happens that 37 is the word counsel, which basically means words 26 and 33 are also represented by vectors of size 112, and the sequences are of 3. Okay, and then you can see the code, pretty much the same code we have, right? Notice that this does a reshape and a split, but there is no transpose, because here you have a little bit more control. Notice that this is exactly the same thing we use. This is the exact same thing we use, right? And here you have the parameters, weights and biases, and all the details in between. So basically, I want you to use this block spot and then solve it with the RNN that we are using. So I think this will help you to clear out a lot of issues. Remember, print out the dimensions with that function that I gave you. I believe the code is, there's a GitHub somewhere in there, but just read through this, and then our plan will be next Tuesday. So this homework is due next Tuesday before class, and then during class, I will solve this problem. Make sense? Everyone? That's it. That's it for today. Sorry I went over 10 minutes. So hopefully then, once we solve this one next week, I think RNNs will be pretty clear, at least for this particular simple example. All right, and I'll try to grade your exam and homework hopefully by Friday, and so you'll have that as well. All right, so please, if you have any questions, ask. Otherwise, we are going to stop here for today, and I will be posting these 2 videos later tonight. Questions? All right, thank you.
Yeah, Professor.
Oh yeah, go ahead, please.
Can you update the requirement of the project on the Blackboard? Because I want to make sure I do it in the
Yeah,
right way.
it's pretty simple, really. I just want you to, I'll do that, but it's pretty simple. Just apply one of the techniques to some data set. You don't have to collect data.
So there's no specific limited of the approach.
No, just
okay.
because you could use an RNN, you could use CN. I have one student just use different data from the one I've used in the class, in labs or homework, right? So
okay.
Find some data set that's as much as data you can, because you want meaningful results. And then definitely don't just do like, a multi-layer, right? So do either CNNs or RNNs or word embeddings. Pick a topic.
Okay.
Got it?
Yeah, got it.
Okay. Any other questions, guys? All right, so we'll stop here for today. Please start working on that homework assignment. I will post the link on Blackboard, and this will be due remember, it'll be due before the class, because during the class, I'm going to go over the solution. Okay?
Okay.
All right, thank you.
Okay. Bye, Professor.
Bye.